Hi everyone and welcome to Arctic Live. It's fantastic to have you with us. Today we are going to be looking at ice and sea level rise in this live broadcast investigation sea level rise. Fantastic to have you with us. We're going to do this lesson in a few stages, and I'll start off in a bit with some housekeeping and a general introduction to where we are. Then we have the amazing Dr. James, a glaciologist, who will be telling us about all the different types of ice that we have in the polar regions. We'll then move into the live investigation stage of the lesson, and we'll be doing that together, and we'll be looking at the impact of different types of ice and whether when they melt, does that cause any sea level rise at all. Time for Q&A at the end, and really great to wrap up any misconceptions that you might have. The science skills we're looking at today are predicting and observing. But before we get into the lesson content, a little bit of housekeeping. So all the Q&A happens with the chat box next to the video stream, and then that is also where the polls will appear. If you want to upvote a question rather than asking another one yourself, please feel free to do so, and you can use the thumbs up icon next to each of those questions. We tend to answer the questions with the most votes first because we reckon that's the one you want answered most. If you do get any technical issues, you can contact support by clicking on the chat icon, and that's the green chat icon on the bottom right of each page of the Encounter Edu website. So a few things just to clarify there. Now, to introduce you to the live lesson, my name's Jamie, and with Ellie, who's behind the camera, we are at the UK Arctic Research Station in Ny-Ålesund in Svalbard. Ny-Ålesund is a settlement, northernmost community in the world. So this way, about 1,200 kilometers, which is about 700 miles. This way, we have the top of Norway, about 700 miles odd. This way, we have the North Pole. We're on this archipelago called Svalbard, and around about us, I think here there are now about 100 or so scientists and support staff, and we also have quite a few NASA scientists up here for a rocket launch. For those watching from America, a lot of American scientists over here at the moment, and the rocket fuel arrived by ship either late last night or early this morning, so gearing up for that rocket launch, I think, in a few weeks' time. But now we're going to have a look at ice. I can certainly see lots of different types of snow and ice just behind me here. But we're going to dial in and see if we can get Dr. James from the University of Liverpool onto Arctic Live. James, can you hear us?
Yes, I can hear you, Jamie. Really nice to be here. About snow and ice.
The polar regions where we are at the moment. I know you've visited these parts of the world as well. Just to start us off, when I look out of my window, I've got a lot of white, and it could be quite easy to think that this is all sort of like it's just snow and ice covering the polar regions, and we don't need to think more in a more complex way about it, or should we think in a little bit more depth?
Oh, definitely. I mean, ice is on the one hand a really weird material, and it's also a really variable material as well. So you mentioned looking outside. So in the ocean just behind you, you'll be able to see sea ice. So this is just the frozen ocean. So this will be relatively thin. I think from what you were saying before, it's probably only going to be a few centimeters thick. You'll also have glaciers nearby. So this is the way in which these are formed are very, very different. This is accumulations of snow that have happened over hundreds, if not thousands of years. And then as the snow has accumulated, it's pressed down and compressed to form solid ice. And then where those glaciers then flow downhill into the ocean, that ice then breaks off as icebergs as well. So in the fjord as well, in the ocean, you'll be able to see some of those whizzing around as well.
We've certainly got some icebergs stuck amongst the sort of pancakes of sea ice. It's quite pancakey out there at the moment. These about sort of 3-4 meters across of sea ice, and then these icebergs a little further away. So just to recap there, we've got sea ice, and that's when the sea itself freezes. That got that right?
Yeah, that's right.
And then we've got land ice, so that's with the glaciers or ice sheets forming, with snow sort of squashing down into ice over time.
Yeah, that's correct.
And then when some of those ice sheets or some of those glaciers then meet the sea, and when they break off, that's where icebergs come from.
Exactly. So just like the glaciers that are behind me in the photo, where you get the glaciers ending in the ocean, that's where they break off into icebergs and then can travel on their way into the open ocean as well.
We have a seasonal sense, especially if we live in sort of like more northerly or more southerly, of snow and ice some of the year, and then it completely goes or it goes down to about nothing. When we talk about polar ice changing, do we have the same seasonal variation? I think we've got a NASA graphic of the both the Arctic and Antarctic through the year, and perhaps you can tell us sort of what one would expect to see in these regions as we go through a year.
Yeah, definitely. There's huge, huge seasonal changes that happen in both the Arctic and Antarctic. Just as where you all are at the moment, where you may see the trees going into leaf and sort of like being being very green during summer, and then losing all their leaves during winter. It's very similar in terms of the sea ice that changes that we see in the polar regions. So as things go into winter, things cool down. The sea starts to freeze. The amount of sea ice then expands. It covers a larger area. And then when things start to warm up in the spring and going into the summer, then that sea ice melts and the amount of area that it covers reduces. So the polar regions definitely do have a seasonal cycle of expansion and contraction.
Sort of like have this sort of like this sort of like, yeah, as you say, sort of expansion and contraction seasonally. When we see in the media or in wider public debate this about sea ice loss or ice loss in the polar regions, are we talking about this natural phenomenon, or is there something different? And I think we've if you want to sort of queue up, I think we've got two graphics that we've been talking about, one on Arctic sea ice and one on Greenland.
Yeah, so when we're talking about sea ice loss, what we're actually talking about is something quite different from the seasonal changes. So when we talk about sea ice loss, we tend to use the minimum extent that happens during the year and see how the minimum extent changes from one year to the next. And what we see, especially in the Arctic, is that over the past 30, 40 years, so we've had really good observations from satellites for what the coverage of sea ice has been since about 1979. What we've seen since then is a steady decrease in the amount of Arctic sea ice cover. So it's not the seasonal cycle that we're talking about in terms of sea ice retreat, sea ice decrease. It's the minimum extent, and what we're seeing is the minimum is getting smaller and smaller through time.
Straight line graph. It's a bit wobbly. Is that because nature doesn't behave in a straight line, but we look at an overall trend?
Yeah, so the wiggles in the line, so all good climatologists love a good wiggle. So the wiggles that we see through time, that part of those wiggles is the seasonal cycle, and so where you get expansion of the sea ice through time in winter and the contraction during summer. But then also there's the year-to-year variability. So just as how so some summers aren't as warm as others, and some winters aren't as cold as others. The same happens in the Arctic and Antarctic. But when we look over longer timescales, we look at the trends of what's happening, and that's where we make a distinction between the weather conditions, what happens from one year to the next, and then the climate overall. So the climate is the overall trend, and what is happening over the longer time period.
And we're seeing that trend. I think we've got a sort of animation of Greenland. We're seeing that trend both with Arctic sea ice and with this ice sheet, this different type of ice on Greenland.
Yeah, so the Greenland ice sheets and Antarctic ice sheets. So these are the land-based ice. Just as you get snowfall during winter and then melts during summer, the same happens in Greenland. But because these are big blocks of ice, so the Greenland ice sheet contains about 7.5 meters worth of sea level change, and the Antarctic ice sheets contain around about 65 meters worth of global sea level change. What we're seeing is that we're having more melting of these ice sheets, and then also more retreat of the glaciers and more iceberg production, which means that these ice sheets are actually shrinking and contributing towards global sea level change.
James, amazing. I think what we're going to do now, thank you so much for that explanation. Definitely cleared a few things up for me, and I imagine cleared a lot up for young people watching. We've got a little investigation to do together with the classes watching, and I'm just going to take you guys through what you need for this. The first thing you're going to need are 2 containers, clear containers, and these are going to be our mini oceans. We're also going to need 2 cans, and we're going to use these cans to represent land. So we're going to put 1 in each of the oceans. We'll add water in just a bit. And you're also going to need an iceberg and an ice axe. No, don't worry. You can use what ice you have to hand, but this is where the ice that we're going to be using for today's live investigation came from, as we just went down to the beach earlier today to make sure we had enough ice for you to show you this investigation. Hi, we're on the beach in the Ålesund, up on Svalbard. The research station's just over here. Very shortly, I'll be coming back to do a live lesson for you guys all about sea level rise and thinking about the different types of ice that we have up in the Arctic. Now, one thing we'll be talking about are icebergs, and you can see a couple behind me just beached here, a bit larger one just further out. To do this investigation, you are going to need ice in the classroom. Now, I'm very lucky, there's a bit of iceberg down at my feet. If you don't have any icebergs near you, it's okay to use ice cubes from the freezer. But I'm just going to pick this up. We'll use it in our investigations today, and we'll speak to you very shortly back at the station. The sea level will change as these two melt. Now, we have a poll that we should be able to get up for you, and in that I would like you to think, before this investigation runs its course, before all the ice melts, what do you predict will happen? So you've got one of four choices. The first choice is that melting sea ice and melting land ice, so both of these will cause sea level rise. So we'll see the water level come up above the black line. The next choice is that only melting sea ice will cause sea level rise. So as the ice in the sea here melts, the sea level will rise, only in this one. The third option is only melting land ice, so only as this ice, the Greenland ice sheet or the Antarctic ice sheet melts, will we see sea level rise. Or in fact, that melting ice will make no difference on either of these two, and the sea level will remain the same. So in your classes, thinking about what might happen and making your prediction. So in science, very often what we're doing is we're thinking about an issue, predicting what might happen, and then testing those predictions and see if what we've predicted is something we can observe happening as well. Now, it's very, very cold. It's about minus 20 Fahrenheit, minus 15 Fahrenheit in here. And so we're not going to get much melting going on. So what I'm going to do is go and put these somewhere much warmer and leave you in the very capable hands of James, who will speak to you a little more about his amazing research in Greenland.
Hi everyone, thanks for that, Jamie. I'm James Lee. I'm a glaciologist at the University of Liverpool in the UK, and I have the absolutely amazing job of researching these glaciers for a living. So the main types of glaciers that I look at are the glaciers that end in the ocean and produce icebergs. And the reason for this is that these types of glaciers contribute a huge amount to global sea level change. So, for example, from the Greenland ice sheets, they account for around about 50% of all ice loss from Greenland in the past 20 years. And that ice loss is, at the moment, only around about 13-14 millimeters worth of sea level change. So that might not sound like a huge amount, but the question is, what is Greenland going to do in the future? One of the things that we're looking into is then actually trying to find this out. And on the basis of our current best estimates, that it could contribute up to around about a meter to global sea level change by 2100. If you're living in a mountainous region, you might not think that will make a lot of difference to you. But then if you're living in areas like Florida, New Orleans, Louisiana, also the eastern seaboard of the US, then it can have quite a huge difference. And one of the things that we want to know is basically how fast these things are going to retreat and how much ice they're going to contribute. And when we're doing that, we look into how the icebergs break off. As you can see in the fjords just behind me, that these two glaciers, they're producing quite small icebergs. It's a couple of my favorite bits of terminology, lots of bergy bits and lots of growlers. So there's some of the actual technical names for small sizes of icebergs. But you have areas in other bits of Greenland and then also areas of Antarctica which produce huge icebergs. There was an iceberg that was produced last year that was about the size of Rhode Island in terms of its area. And that can contribute a huge amount of water. They break apart quite slowly. They can drift out into the open ocean. And when they're out there, they cause, as they melt, they can get into shipping lanes and cause risk to ships. So as everyone who's heard of the Titanic will know as well. But as things like the Arctic sea ice starts to melt, we start to get more ships going up into the Arctic, transporting goods between Asia and the eastern seaboard of the US and vice versa. Then those ships going through those waters, they're going to need to know what their iceberg risk is and how to keep those ships safe. So part of my work as well at Liverpool is to try and understand not only how much they will retreat, these glaciers will retreat, but then also what size of iceberg will be produced and then what sort of risk to those ships that they will be put under. So with that, I'll hang back to Jamie. I think he's returned.
James, thank you so much, and fantastic to hear more about it. And I think the crew of the Titanic could have done with your research being around a wee while ago. But amazing work that you're doing at the moment. Thank you all so much as well for being fantastic scientists. So hope that you have got these your experiments set up, and that we'll leave those running for a bit and see how the melt is affecting sea level rise on those too. We've got some questions coming through, James. The first question, amazing question. We talked a little bit about thickness of ice, I think. Why is the thickness of ice important?
So it's really important for a few things. So if we take sea ice first, so sea ice is just floating on top of the ocean, so on top of the Arctic Ocean and then the Southern Ocean down by Antarctica. Ice that's been hanging around for a few years, that's had a chance to thicken up, and then it can be upwards of 30 meters thick. Whereas ice that's only formed during this year, for example, might only be a meter thick. And that's really important when it comes around to summer, because it's relatively easy to, during summer, to melt 1 meter of ice, but it's quite difficult to melt 30 meters of ice. So what we're seeing in the Arctic at the moment, unfortunately, is that we're getting less and less of this multi-year thick sea ice and more of this single year seasonal ice, which then means that when it comes around to summer and everything starts to melt, we can have more and more melt in terms of the area of sea ice, which means that so the Arctic sea ice cover reduces, which is one of the main reasons that from the graph that you saw earlier, that the Arctic sea ice is getting smaller because the thickness of ice isn't what it was. When it comes to ice sheets like Greenland and Antarctica, the thicknesses of ice is really important in terms of how the ice flows. So if you have thicker ice, then it means that it can deform faster, it can flow faster, which then means that you get faster ice. So for example, At the ice front of this glacier here, the ice thickness is about 80 meters, whereas at this glacier over here, the ice at the front, the ice thickness is about 200 meters, and that's all to do with the bedrock underneath the ice. But what that means is that that glacier here, that flows much, much faster than this one. So if in terms of sea level contribution, this glacier, the thicker glacier, is making a greater sea level contribution than this glacier. So it's a fantastic question, and both in terms of sea ice and in terms of ice sheets, the thickness of the ice is really fundamental to understanding how these bits of ice are going to respond to climate change.
Thank you so much. I mean, maybe towards the end we can talk about how you know how thick ice is, but we can come to that in a bit because we've got another couple of questions here. Next question is how much ice is there in the world? I don't know how we measure this, whether it's tons or area but is there a lot?
There's a huge amount. So the number that I know is in terms of how much. So if you melted every single bit of ice on the planet, it would raise global sea levels by around about 78 meters. So there's around about 7.5 meters worth of sea level change in Greenland. In the West Antarctic ice sheets, there's about 5 meters. And in the the East Antarctic ice sheet, there's about 60 meters. And then the rest is made up by all the glaciers that exist in other parts of the world as well. So it's huge, huge numbers, huge amounts of ice. What we also do in terms of when we're measuring ice loss from areas like Greenland and Antarctica is we tend to use a unit of measurement called gigatons. So a gigaton is 1 ton multiplied by 1,000,000,000,000,000. So it's 1 times 10 to the 9 tons, which is an almost unimaginable amount. So if you were to stack everything up like that, then it would be around about 0.8 miles by 0.8 miles by 0.8 miles. So just imagine that put on top of, so just standing outside your classroom, that's 1 gigaton. And Greenland is losing around about 250 of those every year. And Antarctica is losing about 150 of those every year. So it's huge amounts of ice that are being lost.
Those scales are barely imaginable. I think I'm going to have to work it out in elephants or Empire State Buildings or something.
Oh yeah,
true.
Yeah, sorry, go on.
Staggering scales.
Yeah, I mean, when you're there in Greenland as well, I mean, this photo behind me really does not do the scale justice for just how huge these environments are. So this glacier here, the width from one side to the other, that's about 4 miles long. This one is about 2 miles across. And then you see the icebergs as well. So I said that this glacier produces small icebergs. I've been out by the edge of the fjord and seen some of these beached icebergs, and I stand next to them, and it's about a third. I don't even reach a third of the way up in terms of how big they are, and those are counted as small icebergs. So next to the big icebergs, which are literally coming off some parts of Greenland and mostly Antarctica, some of those are hundreds of meters thick. And they're basically ice islands that are breaking off the ice sheet.
James, I've got this amazing question probably from a budding polar explorer. Is I think that what they're getting at is, could we ever go back to the North Pole being able to walk on? Like this idea that, we hear about polar explorers from yesteryear being able to travel with dogs or whatever, but basically on foot. from sort of mainland Canada, Alaska, Greenland to the North Pole. Is that still possible, or is it more of a swim now?
Uh, so, so it's becoming increasingly difficult year by year. So there used to be, up until a few years ago, ice camps. So where scientists would go out onto the sea ice and take measurements and basically camp on the ice sheet, sorry, on the ice cap to do their science. And they've had to stop doing that now because the sea ice just breaks up and there isn't the thickness to be able to support the weight of the scientific camps on top of the ice cap. There's now even, it's possible to get icebreaker ships directly to the North Pole. And in terms of that's going to be like in the future, there's potential for there to be an ice-free Arctic by 2035. In some, if depending on what happens with global greenhouse gas emissions, it may be that by 2035 we have an ice-free Arctic. If we manage to keep the greenhouse gas emissions to lower levels, we can postpone that to around about 2060, maybe 2070. If we really get them down, then we can keep an icy Arctic. But if someone said to me at the moment then that we were going to hike to the North Pole, I would say absolutely not, because it would definitely not be safe.
Thank you very much, and you've really sort of just about sort of answered the sort of next question: is how long will it take for there to be no sea ice all year round? When you talk about an ice-free Arctic in sort of 15, 20, 30, 60 years time, is that ice-free the entire year, or will there still be some sea ice during the winter months with the sort of 24-hour darkness?
Yeah, so when I talk about an ice-free Arctic, I generally mean an ice-free Arctic in the summer. Basically, that there would be very little, if any, sea ice, and you would be able to get normal ships going straight across the Arctic Ocean without any icebreaker support or anything like that. During winter, yes, sea ice will reform. So this comes back to the seasonality that we were talking about before of the winters cooling down and then the summer warming up. But one of the things that is really quite concerning at the moment is we're seeing extreme weather events up in the Arctic. So a couple of weeks ago, up at the North Pole, it was actually above freezing at the North Pole, and this is basically in the middle of winter, and that was due to an extreme weather event. Where as well in the US and Canada, you have these cold outbreaks, these Arctic blasts. That's all the weather that should be over the Arctic. It should be over the Arctic ice cap. But instead, because we've had this weird weather that's becoming increasingly common with climate change, is all that cold air has been displaced and is actually sitting over North America when it should be sat over the Arctic.
Dave, we've got a question here, and I know that on Arctic Live we're covering a lot of this tomorrow with our lessons about caring for the Arctic. You talk about sort of ice melting. What can we do to help slow down melting is the question.
So there's things that, in terms of like stuff that us as scientists do, we produce our research and then we take it to government, to industry, to then basically lobby and then say, these are the changes that are going to happen. And then if you don't do something about it, then it's going to cost a lot more in the long run, both in terms of finance and then people's lives and people's happiness as well. And one of the best things that I think people can do in terms of getting action, because what we're ultimately trying to do is try and get people to reduce the amount of greenhouse gases that are emitted. And that's not, there's stuff that you can do on an individual basis. So things like using as little energy as possibly can. Also things like eating food that doesn't have a big greenhouse gas cost to it. So eating less red meat, because things like cows and lambs, they actually produce a lot of CO2 as part of their lives. Then also things like the things that you buy in terms of like fruits and vegetables and stuff like that. So where they're from. So if you're eating, I don't know, like so for me in the UK, if I'm like having some vegetable that was grown in the US, whereas I could get the same vegetable that was grown in the UK, then the carbon footprint of importing that food from the US is much, much greater than it would be if it was transported from within the UK. But also as well, it's not just, you can't take it can take some personal responsibility, but not all personal responsibility for trying to have this change. A lot of the change needs to be made by industry and made by government. And one of the best ways in which you can deal with that and make sure that it's actually taken notice of is just by talking about it. Talk about it with your friends, with your parents, with whoever you come across, and find out more about it. And by doing that, people will take notice and people will need to respond to that as well. So I think really that is the best way in which we can try and adapt this to this and reduce greenhouse gas emissions, is by talking about it and making sure that the people who are making decisions actually are taking notice of what people are saying.
James, thank you very, very much. Very sadly, that's all we've got time for in terms of Q&A. I'm going to pass back to you as I dash across the base to see what's happened with our experiments. But we'll be checking in just a while to see whether look at our predictions and to see what actually happened, see what we can observe. So I'll see you in just a bit.
So I've talked a lot about what Greenland might do in the future, but then one of the questions that I normally get asked about when I say these things is, well, how do we know about what Greenland and Antarctica are going to do in the future? And what we do as scientists to try and understand that is that we use computer models of the ice sheets, and including all the physics, all the climatology, our best possible understanding of how these systems actually work. And then what we do with that is that we need to make sure that they work as well. And the way in which we make sure that they work is by comparing what the modeled ice sheet behavior is from the numerical models and comparing it to the real world of where we know the glaciers have been in the past and how the thicknesses have changed and how the sea level contributions have changed through time. So I've done quite a bit of work on this in Greenland, where we've been reconstructing what the glacier change for these two glaciers has been over the past 250 years. And the way in which we work that out is, you can probably see from the photo behind me, that there's a bit of light grey here, and then there's some dark grey up here. So the light grey bit here, that actually shows where the glacier was in the past. It's where the glacier has flowed down past the bedrock and eroded out all the sediments in the bedrock as well. So that elevation change is around about 300 meters. If we follow this line all the way down the fjord, then where the glacier is now is about 15 miles away from where it was in 1750. So if you took the world's best long distance runners, it would take them about 2 hours just to run the distance that this glacier has retreated over the past 250 years. And in the intervening time, we know where the glacier has been through lots of different bits of evidence of things like people's travel diaries, things like old aerial photography, and then in the more modern day satellite imagery. And if we run those numerical models, if we run these simulations, and they're able to match up how the glacier has changed through time, we can say, great, the model's working. And what we've found recently is when we've done these tests, we've actually shown that, yes, the physics in the models are working. So fortunately / unfortunately, depending on your perspective, we've shown that the projections for what's going to happen in the next 100 years are actually more than likely not correct. So the estimates of sea level contribution of around about 1 meter change by 2100 seem to be the most likely. So with that, I think Jamie's back, so I can hand him back.
Brilliant, James. Thank you so much, and thank you for sharing with us how sort of predictions work, these models work in the science world, and the whole range of data you can feed into it, not just current observations. But current observations is what we're doing with our little investigation, and I think we can see here we go. We've seen quite a little bit of sea level rise from our melting land ice. With our melting sea ice, I'm just going to peek over, we haven't had any of the melting sea ice. We have had melting sea ice. We haven't had any sea level rise from the melting sea ice. So as we've been learning over the course of today, when we have land ice that melts, that is contributing which we've touched on briefly today, but we'll be covering more of that tomorrow. But very sadly, we've hit our time. Thank you so much, James, for being part of Access Arctic Live today and this live investigation into sea level rise. It's been fantastic hearing your insights, your experience, and some of your adventures too. Thank you all for watching too. It's been great having you with us. But for now, it's goodbye from Arctic Live. Bye bye.